Okay, so in this video, in one way, it's going to be a continuation of what I was talking about in the videos that came before. In another way, it's going to be different, okay? I would think that everybody would see the problems here as being the same as the problems that I was just showing you in the other videos, but I'm going to assume that that might not be the case, all right? And that this really does seem totally different. So I'll try to do this like it's something brand new, all right? Nonetheless, though, when you watch the video, I hope you see that, yeah, this really is just the same concept in the other videos with a little bit different perspective. That's it, okay? All right, so first question to get us thinking about this. Consider the region bounded by y is 3x plus 1, which is this line right here. Y is equal to 2, which is this horizontal line right here. And x is equal to 0, which is also known as the y-axis. Okay? All right. And it says calculate the volume of the solid that's obtained by rotating about the y-axis. Well, that's what makes this different. Up to that point, it probably sounded the same. But if you take this and rotate it about the y-axis, then you're going to get a cone, roughly of these proportions, right about like so. Okay, so you got a cone right there. This way. All right, that's what'll be different about it. Now, okay, so let's say that, fine, all right, we're going to rotate it around the y-axis. That will change the math a little bit. The concepts involved in doing the math won't change, but the way that you look at the information will be a little bit different. There's our formula to find the volume. The lower and upper limit of integration are the span of the object from like y is equal to point A up to y is equal to point B. A of y is a formula that tells you the area of the cross section at point y on the y-axis. Because remember, the framework for thinking about these is that the setup involves cross sections. This is going to give us a cone if we take that triangle and we rotate it around the y-axis. If I cut that cone into little thin slices up and down the y-axis, each slice will be a circle. That's what I'm calling the cross sections. Each cross section will be a circle, and they're going to be different sizes. So you tell me what point you're at, y on the y-axis, and A of y is a formula that tells you the area of the cross section at that point. So with the difference in variables, it should seem the same. All right. Now, okay, so let's say we're looking at this, and we go through our procedure. We say, well, okay, this shape right here, if you take that triangle and you rotate it around the y-axis, say you do all that, then we're going to get circular cross sections. As a matter of fact, they will be circles. Okay? But what will the radius be? Now imagine that I was saying that, all right, we're going to get like this and like this. Okay, we're going to get this cone. It's going to have an opening up there and so on. Wouldn't the radius of any circular cross-section be this distance right here? Yeah. That's like, for the cross-section located at this spot right here, see that circular slice right there? That slice, that circle, cut it, with a knife right here. That circle will have a radius of this distance, okay? That's a horizontal distance. So here's what we got to figure out. Horizontally, how far is it from this point to this point? Is the horizontal distance 3 or 7 or, well, the horizontal distance depends on where you are. But it's the distance from here to this line. How are we going to give the distance from here to that point on this line? Would that distance be the y coordinate of that point? No, that's up and down. Y is up and down. Would this distance be the x coordinate of this point? Yes, x is left and right. Give me the x coordinate of that point on this line, and that will be the radius of the circle that's at that spot. Okay, so we need to solve this for the x to get the radius. If you solve this for x, you'll get y minus 1 over 3. So the radius is going to be y minus 1 over 3. Okay? All right, now hopefully you could like get a sense for the geometry when I showed you in the picture, but let me put this note that all that is the x-coordinate of any point on the line. What was it? Y is 3x plus 1. Okay. So if you said, what's the radius at the point where y is 2? So put 2 in for y. 2 minus 1 is 1 over 3, 1/3. Oh, so the radius at the opening of this cone is 1/3, in other words. Okay, that's what that tells us. You tell me where you are on the y-axis, this will tell you the radius of the circular cross-section at that point. All right, so I got that. Now, so 2, what's the area of any cross-section? Well, I know they're circles, and I formulated a way to calculate the radius up and down the y-axis. So that's going to be pi times the radius, which is y minus 1 over 3 squared, right? So let's say pi over 9. Okay, so we get 3 squared. Y squared minus 2y plus 1. Okay, so there's my formula that will tell you the area of any cross-section. You just tell me its location y on the y-axis, and that will tell you the area of the cross-section there. Remember, the reason that has a variable in it is because the size of the circular cross-sections, they're bigger at the top, they're smaller near the bottom, all right? Okay, so now time for our integral. The volume of that cone will be, so what's the span along the y-axis? Like, where's this point? And where's that point? Where does the line y is 3x plus 1 cross the y-axis? Notice my graph is definitely not to scale, but it has a y-intercept of 1. Okay. And then where's this point up here? Well, that was, in the beginning, that was the horizontal line y is equal to 2. So we want 1 to 2, pi over 9, y squared minus 2y plus 1 dy. So on these problems where we're rotating about the y-axis in that direction, the variable is going to be y instead of x. All right, so dy signifies, so that is in fact my variable. All right, so anyway, if you do this, I thought I would just, since we've done lots of integrals at this point and so on, u substitution, trig substitution, we've done all kinds of integrals. That's what we do in calculus too. But this is a fairly simple integral, and you'll get pi over 27, okay, for your answer. So that's the volume of that cone. All right. So, like, so say I've done that, I've done the calculus. The example I used was just a cone, right? Okay. So, could we verify? Okay, could we verify that? Let's see. Volume of a cone, 1/3 pi r squared h. Okay, so it's going to be 1/3 pi. What's the radius? Oh, well, that's what this does right here. It tells you the radius of any circular cross-section. See at the top there where y is 2? What's the radius of that circular opening there at the top? How far is it from here over to here? Okay, well, remember, I said, well, take the y-coordinate where you are, put it in. You'll get, what, 2 minus 1 is 1 over 3. It's 1/3. Okay, and then how tall is it? What's the height? How far from this point to this point? Well, remember, this point was at y is equal to 1 on the y-axis, and that point at the very top was at y is equal to 2. So the height is 1. So what's 1/3 times pi times 1/3 squared? That would be pi over 27. Okay, so yes, we can verify that. All right, but I wanted to use, I mean, you might say, why are you using calculus to find the volume of a cone? It's unnecessary. Well, sometimes I just want to give you an example to outline something, and I think it's nice to verify it. And it does shed a little bit of light on the way that formula works right there to get the radius of the cross section. So that's why we do that. All right. Now the next problem that I want to do is very much different than this one, but it has a little bit in common. Even it's quite a bit different, but it's got a little bit in common. And I thought we would start by thinking about this. And this just gets your mind thinking the right way. That's what this is going to do. So, fairly simple question, and I think fairly simple answer as well. All right? It says, what is the horizontal distance between the points given below? So this one point's at right 3 and up 7, and this other point is right 9 and up 7. So they're at the same horizontal location. I mean, the same vertical location. They're both 7 spaces up. Well, okay. You might be insulted I would even ask you something so simple, but you'll see why in a minute. The distance between these points is 9 minus 3. So the distance is 6. If this point's 3 to the right, and that's 9 to the right, then their distance is 6. You just take the x-coordinate of this point, and you subtract the x-coordinate of that point. All right? So like I was saying, you might be insulted I would even ask you something so simple, but it has everything to do with this next question. So just kind of have that be on your mind a little bit, and I'll end up showing it to you again when I do this next problem, and you'll see why it's relevant. Okay. Now, imagine this situation. Consider the region contained by the line y is x minus 2, which is this line right here. Okay, y is equal to 6, which is this line right here. Y is equal to 0, which is the x-axis. Okay, that's that line right there. And x is equal to 9, which is this line right here. Okay. So consider that. So that means this space right in there. And it says this. It says, calculate the volume of that solid that you would obtain by revolving about the line y, x is equal to 9. So imagine if you revolve like this, 360 degrees. Okay. And you'll get more of the shape over here, down like this, and right all the way around. Okay, so we are revolving this about this line. So let's go through the normal thought process that I've outlined before. Okay? And then I'll show you why it fits in this video with the first problem and the second problem that I showed you. So say we took this and we revolved it that way. It's if you cut it this way up and down, it's going to have circular cross sections. Okay. They will be circular. Now the second thing is, that's a little bit harder, is what's the radius of the cross sections. Okay. Hold on a second. Okay. So what's the radius of the cross section? So imagine like we're kind of going over like this and like that. All right, this is the whole thing. And then I cut right here and I get a circle. The radius of the circle is this distance. So if you imagine like right here, roughly like there's a cross section. That's the radius of it. Okay? Alright, you might say, why didn't you say this was the radius of it? Well, because I was given these things, and I think it would make the most sense to give the radius in terms of the stuff I was given. Alright? So, if I can tell you this distance here, that's the radius. Now, that's kind of like this problem. Isn't it? How far horizontally is it between those? Takes the x-coordinate of this point minus the x-coordinate of that point. I mean, nobody would deny that. That's about as simple as it gets. So I'm thinking that here's what we do to find that radius. Take the x-coordinate of this point and subtract the x-coordinate of that point. So what's the x-coordinate of this point right here? Well, it's 9, because the x-coordinate of every point there is 9. Subtract the x-coordinate of this point. What's the x-coordinate of that point? Well, it's, I don't know, it's different everywhere. You know, every point on this line here has a different x-coordinate. I can't tell you it's 4 or 5 or whatever it is. I can tell you that on the line y equals x minus 2, the x-coordinate is going to be y plus 2, isn't it? Okay, so yeah, that's going to be the x-coordinate on the line y is equal to x minus 2. Okay, solve it for x. Now, do you see why I showed you this? It's just like this, except for I don't have like a distinct known point. I do know in general from that other example that this x-coordinate minus that one is the distance we're looking for. All right, so there's my radius. Let's see, let's say 7 minus y though, because we're going to get 9 minus y minus 2. Okay, all right, so 7 minus y. And then what's the area of the cross sections? Okay, well, that's going to be pi times the radius squared, given that we found the radius in the previous step. Okay, and then the third step. Now, our variable here is y. Our cross sections are cut up and down the y-axis. It only makes sense to give our radius and our cross-sectional area in terms of y. So this will be an integral that's in terms of y, like that first example, okay? The variable will be y. The bounds of integration are up and down the y-axis. The cross sections are cut perpendicular to the y-axis. That's what this one is like, okay? So my volume will be the integral. Well, the bounds here are the span of this object along the y-axis. So this three-dimensional object right here spans the y-axis from down here at 0 up to 6, okay? So we'll do 0 to 6 like that. All right. And then we get the a of y formula. So our cross-sectional area is pi times 7 minus y squared dy. And in some other problems, I went ahead and I multiplied this all out. All right, but you don't have to. You can do these different ways. It's not like there's only one way for me to show you. So I'll go ahead and I'll leave this one. This is if you want to do this without multiplying all that out, it turns out it's a u substitution problem. It's just u squared du. You'll let u be 7 minus y, and the du will be negative 1 dy. Okay, so you could do it like that. You'll get, for your antiderivative, negative pi over 3, 7 minus y to the third power. Okay? Then we'll take that from 0 to 6. Okay, so you can do it like that. If you're not comfortable doing it that way, well, then you can just, multiply all that out like I did in the other examples. There's nothing wrong with that. Okay, so if we do this all said and done, here's what you'll get. You'll put the 6 in, you'll get a 1 there, you'll put the 0 in, you get 7 to the third power, that's 343. So you'll get 342 pi over 3. Okay, 342 pi over 3. Oh, why leave it like that? Let's see. 114 pi. If we divide it out. Okay. Do you see what's different about that? There's questions you ask yourself when you watch the videos. Do you see why the cross sections are circular? That's probably pretty easy to see. But do you see why the radius I give in terms of the variable y? Okay. Do you see why that has relevance to this very simple question? hopefully that's all you needed for me to get you on board with that. From there, we can probably work it. If you can find part 1, you can probably do the rest of it. Anyway, so final answer, 114 pi.